Hello class. Today we're going to be taking a look at lesson 3.4, which kind of just gets a little bit more into some information about perpendicular lines. So in this exploration, in class, we're going to kind of dive a little bit deeper, take our time, whatever you want to call it, with this activity. But since we're not together, if you're watching this video, we'll just kind of do the best we can. So let's say you draw a line. And let's say you have a point that's not on the line, so it doesn't really matter, okay? So here's my point. Today's lesson is kind of about how do we get the shortest distance, or how do we know what the shortest distance is? So in class, I'm going to have the students take a ruler and kind of be measuring. So if I were to put my ruler like this way, so right here, I'm going to have them measure this and say, okay, this is roughly, 3 centimeters. Clearly, I wouldn't want to go longer because notice that would be more than 3. Let's say I go like this way. If I turn it this way, notice that's probably about maybe 2.2 centimeters. So I would basically be having the kids kind of try to move this ruler around to determine where would the shortest distance be. And what they should be coming up with is that the shortest distance is if you can draw it exactly perpendicular, okay? So if you can get this to be exactly perpendicular right here, that is the shortest distance. So over here, what is the shortest distance? Let's just say the segment perpendicular, okay? So that's really what we kind of want, is we want that perpendicular piece. So if you look down at 3 and 4, 3 and 4 are really the heart of this lesson. This is really the two most important lessons, or 2 most important questions of this lesson. So it says, find the shortest distance from point A to the line. So if you look at point A, and then you look at this line, what would be the shortest distance? Well, notice it would be the piece that's perpendicular. Now, if you want, you can calculate all 3 of these, and then you can see which one calculates to be the shortest, but I promise you it's going to be this one that's perpendicular. And that's kind of what they were supposed to get from doing this activity. All right, so what we need to do is we need to calculate this distance. So I'm going to use point A, and I'm going to use point C. And then using those 2, I'm going to run the distance formula, okay? So just kind of to review, here's the distance formula. We're going to subtract the x's, quantity squared, plus the difference of the y's, quantity squared. So, and remember, it really doesn't matter which one you use as your ordered pair, but typically we would call this x1, y1, and then x2, y2. Just make sure you stay consistent. You've got to use x and you've got to go y, so x, y. All right, so if I plug my numbers in, I'm going to do 1 minus a -3, so that's going to zip zap. And then I'm going to do -1 minus 3, and then quantity squared. So if I work this out, that's 4 squared. That's -4 squared. And then if I add those together, I get the square root of 32, which I don't know off the top of my head, but it looks like it's about maybe, we'll say 5.66. And that would be my final answer. So if you could, go ahead and pause the video here and try number 4, and let's see if you can get the correct answer. Okay, hopefully you paused number 4. Let me just go ahead and tell you that the correct answer is the square root of 5, which is roughly about 2.24, okay? If you got this correct, you can go ahead and fast forward the video onto the next part, but if you did not get it correct, let's go ahead and go through that. So once again, we have point A and we have this line. And so the shortest distance is going to be this perpendicular segment right there. So we want to use those 2 ordered pairs. And then we want to run our distance formula. So I'm going to take the second x minus the first squared plus the second y minus the first squared. So if we work this out, that's 2 squared. That's -1 squared. And just be careful, make sure when you square this, Notice it's in parentheses, so you have to square the negative as well. So -1 squared is just 1, and that's how I got the square root of 5. And then you would probably just want to type that into your calculator, so the square root of 5. And then it's okay, whatever, if you want to round to 1 or 2 decimal places, I think that's fine. And so that would be my shortest distance. And again, this is the main point of the whole lesson. Now, if we turn the page, what you're going to see on this next page is a couple theorems. Now, these 3 theorems that are listed here are definitely theorems that I'm going to admit I have forgotten over years, and I've had to look them up. They're definitely not theorems that you use on an everyday basis or in a lot of your proofs, but they can come in helpful. So really, again, it boils down to how are you going to go on to math, okay? So let's go through them. It says linear pair perpendicular theorem. If 2 lines intersect to form a linear pair of congruent angles. Well, just think to yourself right now, I mean, if you have linear pair, so this is a linear pair. That's a linear pair. But if they have to be congruent, so if these have to be congruent, then doesn't that mean that they have to be 90 and 90? So what they're kind of telling you here is your picture kind of looks like this, is that you have linear pair, but they must be congruent. And then it says, then the lines are perpendicular. So I guess if what I kind of think about is I sort of think about like if linear pair angles are congruent. So basically if you're perpendicular, okay, then the lines are parallel. Or sorry, the lines are perpendicular, not parallel, perpendicular. Okay. And again, this is something that every now and then I have forgot the title. I understand the concept, but sometimes I forget the title of it, and I just have to kind of remind myself. All right, perpendicular transversal theorem. It says in a plane, if a transversal is perpendicular to one of 2 parallel lines. So again, let's say you have parallel lines. We're going to make this easy, kind of try to draw them a little bit horizontal. So you've got A and you've got B, and those are parallel. If this transversal is perpendicular to one of them, so if you think kind of like this, so this transversal is perpendicular to 1. If this line extends, what do you think is going to be what's going to happen right there? And that's kind of what they're talking about. So I would say if A is parallel to B, and we're going to call this T for transversal, and A is perpendicular to T, then wouldn't this also have to form a 90-degree angle? So you would say then B is perpendicular to T. Now again, I'm guilty of forgetting this title from sometimes, and if I get into a real bind and I'm not allowed to look it up, what I'll use is I'll use corresponding. So I'll use the fact that the lines are parallel, and I'll use that these are corresponding. So then this is 90, like 90, and then I can say they're perpendicular. So if you forget this title, you just have to maybe add an extra step onto your proof, so it's not too big of a deal. All right, the third one says lines perpendicular to a transversal theorem. In a plane, if 2 lines are perpendicular to the same line. Again, this is kind of difficult to draw because let's just start with one line. So you've got one line, we'll call it A. It says if 2 lines are perpendicular to the same. That means my picture kind of looks like this, but your markings are slightly different. So if you have 2 lines that are perpendicular to the same, so what they're telling you is this is 90 and this is 90. If these are perpendicular, what do you know about these 2? And notice again, now, in a way, you're using corresponding again, so you're still using corresponding, only this time you're really using the converse. So you're saying, well, if these are equal, then my lines are parallel. Now, this does not necessarily say they're equal. It says they're perpendicular. So if you forget this title, or if you forget this theorem, you just have to add an extra step onto your proof, okay? So let's write down, if A is perpendicular to T, and if B is perpendicular to T, then we know that they are parallel to each other, which again does make logical sense, but we need some type of a justification. So in this section right here, they're trying to get you to determine or come up with a justification using one of your maybe new theorems or an old theorem, is determine which lines, if any, are parallel, and then you have to say why. So if we look at number 5, clearly the only choice would be is P to Q. Those would be the only ones that are parallel. So we look at this and we say, well, this is 90, but we don't necessarily know anything else over here. We don't have any other markings. So I'm going to say, no, we really don't know that these are parallel, okay? So if we move on to number 6, notice there's a clear, obvious choice. Either M is parallel to N and J to K. Like, there's no way J goes to N. So let's just take a look at M and N. So we're going to look at M and we're going to look at N. And we're going to try to determine if we can say they're parallel and if we can say why. So if I look here, I can't really use anything. But notice if I have this. So what you're telling me is you're telling me that M is perpendicular to K, and you're also giving me that N is perpendicular to K. Notice the two perpendicular pieces. So if they're perpendicular to the same line, then shouldn't they be parallel to each other? So we can say that M is parallel to N by the lines perpendicular to a transversal theorem. So this would be my answer, or at least part of my answer, okay? We still need to look at the other two lines to see if there's enough. Now maybe there's not enough, maybe there is, but we have to look at them and see, okay? So let's take a look at J and we'll look at K. Now if we look at J to K, right over here in this section on the right, there's really not enough information because there's nothing here and there's 1, so there's not enough. But when we go over here, notice we have perpendicular again. So we have essentially the same situation. We have J is perpendicular to M, and we also have K is perpendicular to M. We're really using the same theorem. So we can say J is parallel to K, and it's really by the same theorem here. So I would say this is also part of my answer. So yes, I can conclude both of these are parallel by the same justification. So why don't you go ahead and try it here, or stop the video, pause it, and go ahead and try 7 and 8 and see if you can come up with any conclusions. Okay, hopefully you paused it. When I first look at this, for whatever reason, my eyes went to R and S. So if I look at R and if I look at S, I was trying to determine if they're parallel because they look parallel, but I need to make sure I can give a justification. So I've got some marks down here, but I don't have anything up here. So there's really no way for me to justify this statement. I really don't have any way. It surely looks like it, but I can't say for sure. So I'm going to have to eliminate that option. So now let's go to P to Q. So if I look at P and Q, again, up here, there's really nothing for me to go from. But down in this location, I've got some perpendicular pieces. So what I'm noticing is that P is perpendicular to R, and I'm noticing Q is perpendicular to R. So this is the same property we saw before up here. Notice I've got two perpendicular symbols. So if they're perpendicular, then I can say that P must be parallel to Q. In a way, you're kind of almost doing, and I don't want to say a substitution because we are switching out the symbol, but you're kind of like eliminating the repeated piece, and then you're putting those two together. But it's by this same theorem, the lines perpendicular to a transversal theorem. And again, I will definitely admit that I have forgotten these titles from time to time, and I have to remind myself because they're not ones that you use a lot. They come up from time to time. Okay, hopefully you tried number 8, or if you need to, quick pause it here and you can do that as well. My eyes are jumping right to M and N first, so that's the one I'm going to kind of go with. And so what I'm noticing with M and N is at first I'm seeing this, which I'm liking, but there's not really much over here, except for these are congruent. So real quick, I know that M is perpendicular to S. I know that. Like I can tell that it's perpendicular. Is there a way for me to say that N is perpendicular to S? Notice how these are a linear pair and they're marked as congruent. So if we go up to the very first theorem, it tells us that if we're a linear pair and congruent, then the lines are perpendicular. So in order to get this step, I need linear pair perpendicular theorem. Once I've gotten this step, now using that, I can now say that M is parallel to N by this lines perpendicular to a transversal theorem. So once again, we're seeing the same property being used. But really, in a way, both of these two theorems are used to get your conclusion. All right, let's take a look at S and T. So I like that there's a perpendicular symbol here, but there's not one here. So that's kind of a bummer. I like that there's one here, but there's not one here. I need it in both spots. Now I can't really cross. The reason why I can't really do a cross one is because if I were to write this, M would be perpendicular to S, and then N would be perpendicular to T. Whoops, sorry, that's supposed to be a T. Notice there's no repetition. I need essentially S and T to be perpendicular to the same letter. I need these to be the same. I truly don't care which one it is. I just need it to be the same. But if I look at my diagram, there's no way for me to get really a perpendicular symbol here. So I'm guessing that M is not going to be the good choice. So if this is perpendicular, I need a perpendicular here. And I think I can get it by this linear pair perpendicular theorem. So I'm pretty good. I'm feeling pretty comfortable. I think I can do N is perpendicular to S by this, I'm just going to write LP perpendicular theorem. And N is perpendicular to T, pretty much by the given, just by definition of perpendicular. And then notice here's my repeating piece that I can cancel. And so I think I definitely can say that S is parallel to T by this one. So I'm just going to kind of draw an arrow here so I don't have to continue to write. Okay, so I definitely have enough. Now, they're just trying to get you to think about a proof without doing the full-blown step 1, step 2, step 3. But really, you have it. You have your step 1 would be your given, step 2 would probably be your linear pair, and step 3 would be your transversal. So it's not a long proof, it's just you have 2 new theorems here, okay? All right, let's take a look at number 9. Oh, look, there's the proof, okay? So in number 9, you're seeing that it is the actual full-blown proof written out. So let's go ahead and copy our given because we know that that's not going to change. Now, if you did not want to use these new theorems, you would just need to maybe add a few steps and say things like corresponding or different things like that that might be used. So that's just, again, a choice. So we're going to try to use the new theorems and see how it goes. All right, we have 1 is congruent to 2. So that kind of already throws the flag up in my brain because those are a linear pair. C is parallel to D, that's kind of already marked. And B is perpendicular to D, again, that's already marked, so that's good. Okay, linear pair perpendicular theorem. Remember, that tells us if these are a linear pair and congruent, then that means that A is perpendicular to C. So we've gotten that. Now I'm just going to kind of put a little check mark right here because we've kind of used that part of our given up. Now we might still use a substitution, but we've used that part up. Okay, now we have A perpendicular to D. So A right here, how are we going to say that is perpendicular to D? And if you look, it's this one. We haven't used this one, I don't think, in some of our other ones, in our other steps here, just a bit, or a little bit ago in those pictures. So let me just kind of try to walk you through this a little bit here. See, at first you might not know who you're supposed to pair this with. Do you pair it with this one or do you pair it with that one? But notice there's no repeated. There's no A or C. So then I'm kind of focusing my eyes on this. That's what I'm kind of focusing on. And so what I'm noticing is I have C parallel to D. So C is parallel to D. And A is perpendicular to C. Do you notice how the C is the repeated piece? And if we go back to our page here, remember we have this one right there where it says parallel and perpendicular, and then you can conclude perpendicular. So notice what they're getting rid of. Do you see how they're getting rid of the repeated piece? And they're putting those two together. We're doing the same thing here. We're just getting rid of the C. That's our repeated piece. So this is called the perpendicular transversal theorem. And I'm just kind of trying to shorten it just a tiny bit just to save myself some writing. Now we do know what the last line is. A is parallel to B. Now just again, I already used this up, okay? So I guess one thing is you haven't used this part of the given. Typically if they give it to you in the given, you're going to use it. But we need to probably use that. So let's put these two together. Are you noticing the D is the repeated piece? So if D is repeated, notice how they're putting the A and the B together. Again, we have a perpendicular, and a perpendicular goes to a parallel. And that's this one that we've seen on 5 through 8. Two perpendiculars get us to a parallel. So that is going to be the lines perpendicular to a transversal theorem. I'm not going to lie, this is a little bit of a confusing proof. It is. But you just got to kind of keep working through it. All right, number 10. Number 10 is kind of asking you to do a proof only without really, I guess, the box. Because remember, they're going to try to start taking the hints away from you. So if you want to do kind of a full-blown 2-column, make yourself a little chart here. There's a lot in the given, though. There's a lot in here, because it tells you that all of them are vertical. All the verticals are parallel. So there's a lot that you would have to write down. But just, I guess, give it a try, okay? So hopefully you paused it, okay? Oh no, sorry. We're trying to determine if they're parallel. Sorry, I misspoke on that one. I actually just kind of reread it there when I was paused for a moment. So in the given, I guess it's not quite as much. So let me go ahead and just fill the given in. I've got a perpendicular here. I've got a perpendicular there. I have a perpendicular down here. And one here. That's just a lot of perpendiculars. Oops, forgot my symbol. And then it looks like I've got 1, 2, 3, 4 perpendiculars, and I've got a parallel. So I've got E is parallel to F. So that would be our given. Now remember, our goal is to try to basically say that this is like it's like A is parallel to B is parallel to C, and C is parallel to D. That's kind of like the goal. So in a way, that should be your last step. It's just we don't know how many steps it's going to take us to get there. We already have E to F, which we don't really need, so that's not going to be part of our last statement. Okay. So what I'm noticing, again, I'm going to try to look for any type of pattern. Whew, right there, look at that. Look how beautifully those lined up. Do you see that repetition with the E? Do you see how these are repeating? So if these are perpendicular to the same part, then couldn't we say that A is parallel to C? So if they're perpendicular to the same piece, then we can say A is parallel to C, because again, we've got these two perpendicular pieces. So now we might add more in, but I'm going to go ahead and write this down. Lines perpendicular to a transversal theorem. All right, let's do another one. We've got these two. If we look at those, notice again, we've got this repeated piece. So in the same line here, we can go ahead and say B is parallel to D because it's the same justification. So I'm doing really good. I've got lots of pieces here. The only problem is I kind of need to I need to get all four of them. So let's see how we could get all four. If E is parallel to F, let's see how we can maybe use that. If E is parallel to F, then doesn't that mean with these two, E is parallel, wouldn't that mean that C has to be perpendicular? Okay, let me just write down some thoughts here. C would have to be perpendicular to F. If I have another highlighter, I'm kind of trying to use this concept right there. That C is perpendicular to F because, again, I'm noticing the repeated piece. And so that theorem is this one, the perpendicular transversal theorem. Now, we might add something to that, but let's just get this down so we don't forget it. Perpendicular transversal theorem. Okay. So I'm liking this because now I'm noticing my C's, but I kind of think I need something with A. I need some more stuff here. So I think I need A to F. And sorry, I don't have another highlighter here. I'm gonna have to go back to like yellow. I only have 3 highlighters here. Or maybe I can use my pen. I'm noticing this one right here. I'm noticing E and E. So if I can do this one and this one, that means if I cross those out, that also A would have to be perpendicular to F. Yep, so A would be perpendicular to F. Oh, perfect, because look at how nicely this works out. Do you see the F's? So if these are perpendicular to the same line, I can then say that C is parallel to A because they're perpendicular to the same line. So if they're perpendicular to the same line, then they have to be parallel to each other. So I'm noticing it's that theorem again. The line's perpendicular to transversal theorem. And really now, oh, I already had that. I already had that one. I already wrote that down, so I guess I don't really need that one again, did I? I need to get C and D. I think, did I say, okay, so I'm just kind of, again, thinking through my thoughts here. If C is perpendicular to F right here, if C is perpendicular to F, so maybe I just used the wrong combination. So C is perpendicular to F. C is perpendicular to F. Yeah, I used the wrong combination. I apologize. Let me, hold on, I will quick grab a red pen, hold on. Sometimes that happens. The only negative is that I was using a pen. If I was using a pencil, I could have just erased it, but because I was using a pen. But you know what, to be honest with you, I'm glad I did that, because you can see that sometimes I make mistakes too. I don't always have the answer key in front of me. Sometimes I make mistakes and you gotta backtrack, okay? So remember, what I'm looking for is I'm trying to make the transition here to here, or vice versa. I can either do A to B, A to D, or C. I just need a transition here. So what I'm noticing is that my eyes caught this one and my eyes caught this one. Whoops. Because notice I could get rid of the F and I could go C to B. So I should have done C to B. Now I've bridged this gap. Now I've bridged the gap. Perfect. Now that I've bridged the gap, I can say they're all parallel to each other. Do you see how I kind of slip that in? And then I can do D. And honestly, this is just substitution, because all you're really doing is you're just, again, you're kind of like you're pushing them together. You're just kind of substituting. Now, some people might probably want to use the transitive to parallel property that we had. Again, I don't love transitive, but if you want to use it here, it probably might apply a little bit better because it's got the word parallel in it. But substitution is also kind of what you're doing. So these are some difficult theorems. They really are, but you got to be patient and you got to try them, and you got to notice these kind of patterns, which notice how many colors I'm using and different things like that. So really, really take your time and go through them. But that concludes the 4th lesson.